Okay, so this is Chapter 5, Gases. And actually, I think this is a pretty straightforward unit. It's just a lot of math, but easy math, and using various gas equations depending on the information that you're given. So tonight we're going to talk about the first three concepts: kinetic molecular theory, understanding pressure and its units, and Boyle's, Charles, and Gay-Lussac. Probably won't talk about Avogadro tonight. So let's start with a review of the kinetic molecular theory of gases. Breaking down the name, we know that kinetic means motion. We also know that molecular refers to molecules, especially after just finishing bonding. We should know that. So when we put that all together, the kinetic molecular theory is really the moving molecule theory. All molecules move, we know that. And in three different states, we know that solids move vibrationally, meaning that they vibrate around a fixed point. Liquids roll past one another. And gases move in constant, random, straight line motion. And I'm going to fit that in straight line. And how fast do they move? Well, if you've taken physics or you're taking physics now, you've probably already used the equation KE equals 1/2 mv squared. And you would solve for velocity. There's also another equation, and that's KE equals 3/2 RT. So let's talk about the two of these. First of all, you know that the m in the 1/2 mv squared is mass. You know that v is velocity. And on the right-hand side, R is the temperature. So this is temp in Kelvin. And the R is a gas law constant. And that R equals 8.3145. 8.3145, and that's joules per mole dot Kelvin. That is the gas law constant. Now, there is another gas law constant, which I'm going to tell you about right now, and that is 0.0821. But the units for that are liters dot atmosphere mole dot Kelvin. And we're going to use the 0.0821 gas law constant when we use PV equals nRT, or perv nert. So it really depends on the formula that you use. As you can see by the units, one has joules in it. And that's going to be very important when we're talking about velocity, because kinetic energy is measured in joules. So we can actually determine how fast gas molecules move using the two equations by setting them equal to one another. Now, I don't expect you to be able to derive the equation that I'm ultimately going to come up with right now, but I'm just going to show you how it's done. So if you really don't want to write this part down, it's fine. It is in the book, though. So we have KE equals 1/2 mv squared, and that is equal to 3/2 RT, which is equal to KE. So these are going to cancel. We know that our 2's are going to cancel. So we're going to be left with mv squared equals 3RT. In solving for velocity, and I'm also going to take the square root of that right there because my m's are going to cancel. So I'm going to get v equals the square root of 3RT over m. And the m is equal to mass, and that's going to be measured in kilograms. Now, this is going to come up, the reason why I showed you that, because that's how we solve for velocity. And maybe there's a formula like that in physics, not sure. You know my interest in physics, very little. Sorry, Quinn. But on our reference table, okay, on our reference table, it's URMS. So I'm going to see if I can fit this in somewhere. Going to the next page. I'm going to fit this in over here. So on our reference table, it's URMS. Root mean square velocity. Equals the square root of 3RT over m. So again, it's kind of back to like when we were talking about electromagnetic radiation and we were calculating frequency and wavelength, and we use the symbol nu and the physics use the symbol F. It's kind of something like that. So I just wanted you to see the relationship between the two equations. So find the velocity of an oxygen molecule in this room. So let's say that we are given a temp of 20 degrees Celsius and an oxygen molecule. So we know an oxygen molecule is approximately 32 grams per mole, right? And we're going to use this formula, so we know mass has to be in kilograms, so that's going to be 0.032 kilograms. And our temperature needs to be in Kelvin, because whenever we work with gases, ever we work with gases, our temperature must always be in Kelvin. So if you didn't hear that, whenever we work with gases, temperature must be in Kelvin. So that's going to give us 293 Kelvin. So let's use our formula. We've got the square root of 3. Our R is going to be 8.3145. I'm going to use the units so that I can show you what's canceling. I like to write the units separately, actually, just because they're a pain in the butt. And our temperature, 293 Kelvin. And then we have our mass, 0.032 kilograms. Per mole. So we can see that, let's see, moles canceling, Kelvin, Kelvin, and that's going to leave us with joules per kilogram. So when we do the math on this, this is going to be equal to approximately 478 joules per kilogram, which is equivalent to meters per second. Okay, so that's how we would use that. Let's move on. So let's start by talking about effusion. Effusion is how fast molecules can move through a hole. So basically, if I have a box with a hole in it or a divider with a hole in it and I've got some gas molecules on one side, it's how fast these molecules are going to move through that hole to the other side. Which is much different from diffusion, which is how fast molecules spread. From high to low concentration. So if I have a bunch of gas molecules in the corner of the room and I release them, how fast are they going to go from an area of high concentration to an area of low concentration? So Graham's law, we're going to talk about it conceptually first, and then we'll talk about the equation, is basically related to effusion. We talked about diffusion because effusion and diffusion sound a lot alike, but they're really not. So we wanted to make sure that you understood the difference between the two. But Thomas Graham, who was this Scottish chemist, who was the one that experimented with this, found out that the effusion of a gas is inversely proportional to the square root of the mass of its particles. So basically, stated in another way, the relative rates of effusion of two gases at the exact same temperature and pressure are given by the inverse ratio of the square roots of the masses of the gas particles. So let me explain this first conceptually. If I have a small molecule versus a big molecule, what do we know about their kinetic energy? Clearly, you know that KE equals 3/2 RT, which, by looking at the formula, you know that they will have the same kinetic energy. Don't confuse this with speed. They're going to have the same kinetic energy. Kinetic energy is strictly dependent on temperature, not size. But my small molecule, right, is going to move very fast, right? And my very large molecule is going to move slow. So one will go further distance than the other, but they will have the same kinetic energy. So when we look at this actual equation, what we have is the rate of gas 1 over the rate of gas 2 is equal to the square root of molar mass 2 divided by the square root of molar mass 1. where mm2 and mm1 is the molar mass, as I just said. It helps when you're looking at this, if you have the rate of gas 1, designate that as the lighter gas, and gas 2 the heavier. So let's look at a sample problem. Calculate the effusion rates of hydrogen and uranium hexafluoride. So we've got hydrogen gas, which is H2. We've got uranium hexafluoride, which is UF6. So this is going to be approximately 2 grams per mole. And uranium, you've got uranium's 238 plus 6 times 19, approximately 352 grams per mole. So remember I said lighter versus heavier. So rate of gas 1, so we're going to put rate of HE, and then rate of UF6 is equal to the square root of 2. So 2 is 352 over the square root of 2. So that's 13.3. So what does that tell me? It tells me that H2 travels 13.3 times faster than UF6. That's it. That's all it tells me. So that's what Graham's law is all about. All right. Reviewing the meaning of temperature, you already know what this is. Temperature is the average kinetic energy of a molecule in a sample. So now we're going to talk about pressure. So pressure is caused by collisions with its container. And pressure is measured with a barometer. And actually we have to get the barometric pressure for the lab that we're doing right now. All right, so we have 2 different manometers here. That's what these are called. Notice in the first one, the atmospheric pressure is greater than the gas pressure, where H is the height of the substance in the tube. So to figure out the pressure of the gas, on the left, we would take the atmospheric pressure, PATM, and we would subtract the height. Whereas on the right, you have the pressure of the gas is greater than the atmospheric pressure, so the P of the gas is equal to pressure, atmospheric pressure, minus the height. And I know it says it on the bottom of my diagram, but it's hard to read on your printout. We also have what's called a Taurus barometer, and that's because it was a guy named Evangelista Torricelli that invented it in Italy. And what he has is an inverted tube with mercury, and this is a dish that has mercury in it. And as the atmospheric pressure pushes down on the mercury, it pushes it up in the tube. And then you can measure the height of the mercury. And at sea level, as you can see, that is 760 millimeters of mercury, which is also equal to 760 torr, after the guy, Torricelli, which you also know is equal to 1 atm. So these are 3 equivalents that you need to know. And that's written there. And the last one is the 101.3 kPa. All right, so let's do a conversion. Oops, you're missing the practice, I think. Hold on. Okay, so I don't know what happened with my slides, but they're a little bit out of order. So I'm going to explain the next thing, and then the practice will come and you can go back up and fill that in. So first of all, this slide actually appears in a page or two on yours. Wilson at the top of Pikes Peak and Wilson at the beach. So I will come back and explain that. So we're going to move on to Boyle, Charles, Gay-Lussac, and Avogadro's law, but I don't think we'll get to Avogadro's law. So in Boyle's law, this is the relationship between pressure and volume. So what we have is, if we were to draw this out, here's our pressure, here's our volume. Remember, as we change the volume of a substance, that's going to affect the pressure. So it looks like this. It's an inverse relationship. So as volume decreases, pressure increases, and vice versa. If we were to do a graph of P and 1 over V, that would give us a direct relationship or a constant. So the constant would be equal to P times V. This gives us P1 V1 equals P2 V2 as an equation if we were just dealing with pressure and volume at a constant temperature. So this assumes that temperature is constant in this scenario. In the next scenario, volume versus temperature, which is Charles. Okay, somehow the practice got cut out of mine. So let's just do a pressure conversion practice. So let's convert 0.526 atm to kPa. So all we're doing is using conversion factors. So 0.526 atm. And what do you know? You know that 1 atmosphere is equal to 101.3 kPa. Easy enough, right? That's going to come out to be 53.29 kPa. Another one is if I wanted you to convert torr. So let's say 523 torr to ATM. 523 torr, you know that 760 torr is equal to 1 ATM. So your torrs cancel, and you're left with 0.688 ATM. So some pretty basic dimensional analysis, but just using pressure. Okay. I seem to be missing the Charles's versus temperature gas laws. I'm missing a little bit in my PowerPoint here. I'm going to check one more time. So what we have here are 3 different chambers. And we have one at 0 degrees Celsius, or temperature equal to 273. We have one at negative 136.5 degrees Celsius, or negative 136.5 Kelvin. Or we heated this one up on the end. 273 Kelvin is 546. 273 Celsius is 546 Kelvin. So look what's happening to the volume as we increase the temperature. It is increasing, which is a direct relationship. So here, as we increase T, we wind up with an increased volume. So here we have P1 over T1 equals P2 over T2. I'm sorry, V1, not P. My bad. V1, V2. And this is assuming that we are at constant pressure. All 3 chambers, anyway, are in the same area. And the last one, pressure versus temperature, gives us a graph that is also direct. As we increase the temperature, we wind up increasing the pressure. So if this could be an aerosol can in a fire. So P1 over T1 equals P2 over T2. If we put all these together, we wind up with what you learned last year, the combined gas law equation. P1 V1 over T1 equals P2 V2 over T2. So this brings me to my Mr. Wilson at the top of Pikes Peak, which is in Colorado, versus Mr. Wilson at the beach. So, for example, let's say that we had Mr. Wilson at the top of Pikes Peak. The pressure is 470 torr, and the temperature is minus 20 degrees Celsius, and Mr. Wilson, which is the balloon, is equal to 2 liters. Then Mr. Wilson goes to the beach and the pressure is equal to 760 torr, and the temperature is 30 degrees Celsius. What will be the size of Mr. Wilson? Now, a couple of things. Remember, your temperature has to be in Kelvin, so negative 20 degrees Celsius is going to equal 253 Kelvin, because Kelvin equals Celsius plus 273. Oh, wrong button. Here we go. And 30 degrees plus 273 is going to be 303 Kelvin. So we've got our P1, V1, T1 equals P2, V2, T2. So 470 times 253 over 2 equals 760 times X over 303. And then when I solve, I get X equal to 1.48 liters. So let's think about this. Does this make sense? It was warmer at the beach, so you would think that the volume would increase. However, your pressure went from 470 torr to 760 torr. So we didn't change the temperature appreciably compared to the pressure. So these are some things that you have to look at or think about when you're answering questions. All right, let's do another practice question. Okay, so next is deriving the ideal gas law. You can take a look at this. It's on pages 218 and 219. You're not going to have to do it, but if you like all that, I showed you how we derived the one equation earlier, but for the sake of time, I'm not going to do this. I'm not going to ask you to derive it, but it will show you how we get PV equals nRT, where P is your pressure, V is your volume, N is equal to your number of moles of gas. R is your gas law constant, the gas law constant that we talked about earlier. That's the 0.0821, because now we're using units of liters, atmosphere, moles, Kelvin. Sorry about that. My handwriting's a little sloppy tonight. Alright, so let's try a problem here. Example, Wilson is filled with oxygen gas. He has a volume of 3.25 liters at 22 Celsius and 0.75 atmospheres. How many grams of oxygen are in Mr. Wilson's head? Yay. Alright. So PV equals nRT. So what do we know here about this problem? Well, we know the pressure is 3.25 liters, atmospheres, 0.75 atm times 3.25 liters. We don't know our moles. We know our R is 0.0821, and 22 Celsius plus 273 is 295 Kelvin. Yes? Good. So when we solve for N, we're going to get N is equal to 0.1006 moles. And you know that 1 mole is equal to approximately 32 grams. Moles cancel, and I get 3.22 grams of O2 in Mr. Wilson's head. Alright, I just want to show you something up here because I was being lazy and I didn't write units, but we've got ATM times liters equals moles. I'm not going to have enough room here. Let me move this over. So 0.75, we got ATM times liters equals moles. And then we have R times, which is liters dot ATM mole dot Kelvin. And that's times Kelvin. So Kelvin, Kelvin, ATM, ATM, liters, liters. And we were solving for moles. Okay, so we've got 2 problems left. So we are back to stoichiometry, which is kind of nice because we have the final coming up and we haven't done a lot of stoichiometry lately. So although it's gas stoichiometry, it's going to get you thinking in that dimensional analysis frame of mind again. First thing you always want to make sure is you have a balanced equation. Label what you know and what you don't know. Use PervNert to solve for either volume or moles in the equation, and then use dimensional analysis to determine the answer. Sometimes it says steps 3 and 4 are flipped. Sometimes you have to do some dimensional analysis first in order to use PervNert, and that's going to be basically depend on what you're given. So solid potassium chlorate, KClO3, decomposes to produce potassium chloride and oxygen gas. So before I do anything, I want to write an equation. So I have KClO3. Now we're getting to the fun stuff. Decomposing into KCl and O2. So first thing I want to do is balance my equation. I see that's going to be a problem because I got 3 O's and 2 O's. So it means my least common multiple is going to be 6. So it's 6 there, 6 there, and I need a 2 there. And now I'm balanced. What volume of gas? So right away, I don't know my volume. Measured at 40 degrees Celsius and 655 millimeters of mercury. So my T equals 40 Celsius. My pressure equals 655 millimeters of mercury will be produced when 13.5 grams of potassium chloride are decomposed. So I got a lot going on. So right off the top of my head, this is what you should be thinking. First, you should be thinking that you need this in Kelvin. So 273 plus 40 is going to give you 313 Kelvin. That's the first thing. Second thing is, you know that you're using PervNert, right? So, and they want oxygen gas. So we're solving for volume, so we need moles of oxygen. But I don't know my oxygen. I only know my potassium chlorate. So in this case, I'm actually going to have to start and use number 4 first. I'm going to have to use some dimensional analysis because I can't solve the problem until I know moles of oxygen gas. So let's do that. I've got 13.5 grams of KClO3, and I know that 1 mole of that has a mass of 122.553 grams. So that's my KClO3. And in my equation, I have 2 KClO3, and I have 3 O2. And that's my moles. So that's going to give me grams, that's going to cancel, moles is going to cancel, and I'll be left with moles of O2, which is going to be 0.165 moles of O2. So we just did some review of dimensional analysis there. So now I know my moles of O2. So let's see if I'm ready to use my formula now. So PV equals nRT. Pressure, I've got another snafu here. 655 millimeters of mercury. I need it in atmospheres. All right. Nielsen's going to be lazy. I know in order to get from, I'm going to show you over here, but I'm doing it in my whole equation because I'm going to be lazy. So 655 millimeters of mercury. You need that in ATM because our R constant is an ATM. So 760 torr is equal to 1 ATM. So you have to do more dimensional analysis. So I'm just going to do this. I'm going to do 655 divided by 760 in my equation times X equals 0.165, right? And that's moles, times 0.0821 so this is liters dot ATM mole Kelvin, and that's times 313 Kelvin. So my Kelvin cancels, my mole cancels, ATM, and this is going to be ATM over here when all said and done, cancels. So I'll be left with liters, which was what I want. So volume equals 4.19 liters. If you want to find the ATM first and stick it in, you can. I'm just being tired and lazy. Alright, let's finish up with one more problem and that's it. Okay, so in this second example, we're going to use the combined gas law first, and then we're going to use some stoichiometry. So we've got phosphorus plus O2 yielding P2O5. We need to start with a balanced equation. So therefore, 5 oxygens, 2 oxygens, we got to make that a 10, 10, and this is going to be a 4. Let's write down what we know. We have a volume of 82.54 milliliters. We have a temperature of 6,000 Kelvin. We have a pressure of 45 ATM. And they want to know grams of P2O5 eventually. But we're starting with oxygen, so we're going to have to find moles of O2. So we're going to start with PV equals nRT, and our pressure is 45, our volume is 82.54. We don't know our N, our R is 0.0821, and our temperature is 6,000 Kelvin. So when we solve for N, we get 0.00754 moles of O2. I just want to do the units up above so you can see them. So I had ATM times liters equals moles, and that was times liters times atmosphere mole dot Kelvin, and that was times Kelvin. Okay. But now that's moles of O2, and we need grams of P2O5, so we need to do some dimensional analysis. 0.00754 moles of O2, and in the equation we have 5 O2 going to 2 P2O5, and we know that 1 mole of the P2O5 has a mass of 5 times 16 plus 2 phosphorus, 142 grams. So moles cancel, and you're left with 0.428 grams of P2O5. So in this problem we used Pervner first, then did dimensional analysis. In the last example we did dimensional analysis first and then Pervner. So bottom line is this is the new formula, and we showed how we got to the combined gas law through Boyle's law, Charles's law, Gay-Lussac's law, which brought us to PVT equals PVT. And then from that we can derive the ideal gas law, which was what we just used. We talked about pressure, we talked about the difference between diffusion and effusion, and the kinetic molecular theory. And in the next lesson we will finish the rest of the important stuff.